Applications in business and economics. Now, this is really just one application we're going to talk about, and that's elasticity of demand. If you've heard the term elastic product or inelastic product before, we're about to define what that means mathematically. So in a product with elastic demand, consumers will reply to changes in prices. If the price goes up too much, demand will go down. So this is like a regular product that you can get at the store in a competitive market. If the price of one bag of chips doubles some certain brand, nobody's going to buy that bag of chips anymore. Okay, so that's what an elastic product is, or a product with elastic demand. So every product, I suppose, is a little bit elastic, but it changes from product to product. So if you have a medical supply like insulin, and they raise the price of insulin, now that's a terrible thing to do, but either way, the demand won't really go down because that's something that people need, and if it's saving their life, they're kind of willing to pay for it. I first heard of the concept of elastic and inelastic products from the HBO show The Wire. And I guess that's how I remember it, is that in that context, drugs are an inelastic product, specifically heroin. If you raise the price, demand won't go down because they're addicted. Okay, so that's just how I remember it. So however you remember the difference between inelastic and elastic. If it's elastic, people are going to go somewhere else for it. All right, so we put a number on this elasticity, and here's just a formula from economics that economists kind of agree on. I'm not going to derive it because it's complicated and you don't really care. So we put a number to this elasticity as follows. So if we're thinking of Q as a function of P, just for these purposes, we've seen in the past, sometimes we go the other way around, but price and demand are obviously interrelated, so you can think about it as working both ways. So that's the demand for Q units at the price point P. Then we think of the elasticity of demand, and we use the Greek letter, that N thing is the Greek letter eta, ETA. You don't have to know that. You can honestly just write N. This is the Greek letter we use for elasticity of demand. So I don't care if you know the names of Greek letters. So we define N as negative P over Q. So negative price over demand times dQ dP. That's the same as Q prime of P. Like the derivative of Q with respect to P, the derivative of demand with respect to price. Okay, so keep that formula handy. You don't have to memorize it. Example. We're going to find the elasticity of the demand function 2p plus 3q equals 150. We're going to find it and we're going to interpret it. Because if it's just a number, like if the elasticity is 500, what does that even mean? So is that very elastic? Is that good? Is that bad? Right? So we're going to find and interpret it. Let's look at the graph of this demand function first. So price is going to be the x-axis and demand is going to be the y-axis. So notice that as price goes up, demand goes down. And that's going to be the same for all of these functions, right? You're not going to really raise the price and then demand's going to go up. Like more people are going to want to buy it, right? And so you can see, so just think if the price is very low, about 50 people are going to buy it, right? As the price goes up, less and less people want it. If the price is like 75 bucks, it looks like, no one will buy it, right? It would just sort of really stop there. Right, so all of these, some of them will actually be curves. This is just a line. All of these demand curves will be decreasing functions, right? So, but it's not just constant. If it was just the slope of that line, then it would be simpler. And it's not, right, it's not, so it's not the same thing as just a derivative. It's going to vary across that curve. So there's going to be points on that curve where it's more elastic than other points. And remember, more elastic means if you raise the price, like let's say 1%, maybe like more than 1% of people are no longer going to buy it. So it's all based off like a percentage price increase, you get this percentage demand decrease. That's what elasticity is. So we use the formula. To even do that, we need dQ dP, and the easiest way to get that is just to solve that little equation for Q. I could have just given it to you in terms of Q in the first place, but I didn't. If I did, you could skip this step. So just a tiny bit of algebra. 3Q is 150 minus 2P. Divide both sides by 3. Q is 50 minus 2/3 P. So you can think about it as Q of P. We're kind of doing implicit differentiation here, but P is just our independent variable now. So it's just like X. So the derivative of 50 minus 2/3 X is just minus 2/3. All right, so that's the slope of that line, right? That's all we discovered there. The derivative of a line is just its slope. So the slope of that line is negative 2/3. And right, that was like y equals mx plus b form we just put it in. But the elasticity at any point along the curve is negative p over q times that slope. So using, again, you can just write n if you want. I'll know what you mean. So that's 2p over 3q. So at every little point along that line, there's a p coordinate and a q coordinate, right? It's just the x and y coordinates. You punch those coordinates into that formula, and that gives you the elasticity. So that's what I mean. As p and q vary and kind of trade on and off, this changes. So there is indeed like kind of a sweet spot where we have maximum revenue, but we'll get to that in a minute. Okay, now use that little formula we're going to find the elasticity at a couple points, and we're going to say, okay, what do these numbers even mean? Like, what are the units of elasticity? So this is a point on the line when P is 15, Q is 40. So 2 times 15 is 30, 3 times 40 is 120, so that's 0.25. So back there at the point 15, 40, the elasticity is 0.25. All right, now we're going to go farther down the line. So this is the price is higher now. The price is very high and almost nobody's buying it. So when the P is 60 and Q is 10, you have 2 times 60 is 120, 3 times 10 is 30, so 120 over 30 is 4. So now we have very high elasticity. And what that corresponds with is a little bitty change in price you're going to lose a lot of demand. Now we're looking at this point, which I picked on purpose, obviously, when P is 37.5, Q is 25. So that's kind of right in the middle. We're charging $37.50 for our product, and 25 people are buying it. So 2 times 37.5 is 75, and 3 times 25 is 75. So would you look at that? The elasticity is just 1. So that's on purpose, and now let's interpret. Here's how we interpret these numbers. If n is 1, and I should point out that n is always positive. So if n is a decimal, like 0.25, and if n is less than 1, that's inelastic demand. So again, think like insulin. If you increase the price by, let's say, 50%, you're going to lose less than 50% of your customers. That's what we mean by the percent decrease in demand is less than the corresponding percent increase in price, right? Because demand and price don't have the same units. You can't just say if you increase the price by $5, you're going to lose 5 customers, right? It's based on what it is at the moment. So it's right. So if I even increase the price by 1%, I'm going to lose less than 1% of my customers, which is good. That leads you to believe that you might want to do that, right? It's probably going to work out pretty good to raise the price a little bit if you're going to lose less than that percent of demand. Okay, so that's if n is less than 1. If n is bigger than 1, your demand is what we say elastic. So if n is 4, like it was in part B there, if you increase the price by 1%, you're going to lose more than 1% of your demand. And the bigger that number is, you're going to actually lose a lot more than 1%. So you might think, hey, maybe don't do that, right? Maybe back it up a little bit, because if you then decrease the price a bit, it might be worthwhile for the demand you get. Okay, so n can be any big old number, right? There's no cap on elasticity. Okay, and speaking of sweet spots, if n is 1, that's what we call unitary elastic. And the percent decrease in demand is going to be pretty much equal to the percent increase in price. So in other words, if my thing costs $100 and I raise the price $5, that's a 5% increase in price. You are going to lose exactly 5% of your demand. So it's like an equilibrium point where whatever percent you increase the price by, you're just going to decrease the demand by that same exact percent. So you might think, hey, that's a good place to be, and maybe that's where I want to set my price. That's right. That's right. Okay, let's do another example. It's a little bit more complex of a function. So the demand for a product is given by this relationship between price and demand. It's P plus 1, price plus 1 plus, times the square root of Q plus 1 equals 1,000. So I think we'll look at the graph of that because you'll see that it looks similar to the last one. So first, let's find the elasticity. This is the same as the last problem. It's just it's a little more complex of a function, obviously. So unless it's given to you as Q equals some function of P, you're going to have to do this step first. So solve for Q. So divide both sides by P plus 1. Square both sides to get rid of that radical. So Q plus 1 is 1,000 squared over P plus 1 squared. In one move there, I just subtracted 1 from both sides, and I just squared 1,000. 1,000 times 1,000 is 1,000,000. So Q is 1,000,000 over P plus 1 squared minus 1. I could have just given it to you like this, but I like to make you do algebra. Okay, so the only thing we need to get that elasticity really is dq dp, so just the derivative of this with respect to p, and then remember it's times minus p over q. Okay, so that's one, so I rewrote it because now we have to take the derivative, which I think is good. So I just rewrote q as 1,000,000 times p plus 1 to the negative 2 minus 1, because now I have to take the derivative using the power rule. All right, dq dp is the same thing as q prime. So the negative 2 comes out, and that makes a negative 2,000,000 times p plus 1 to the negative 3. Now let's think about something for a minute. I said that elasticities are always positive. This thing, dq dp, if our function is decreasing, which these demand functions have to be because as price goes up, demand goes down, then its derivative is negative, right? So these derivatives are actually always going to be negative. Now, the p and the q coordinate are always going to be positive because price and demand can never be negative. So that's why there's that negative in the formula for this. It's negative p over q times this thing, which is also always negative. So it's not just like something we say. Elasticity is always positive. You can't have negative elasticity because of the way we have it set up and because of the fact that price and demand are always positive. But this thing is always negative because demand decreases as price goes up. Okay. Okay, so that's it. No reason not to rewrite that as negative 2,000,000 over p plus 1 cubed, because now we have to use it and do stuff with it. So that's not the elasticity. The elasticity is that times negative p over q. All right, n is, I'm just going to call it n, is negative p over q times 2,000,000 over p plus 1 cubed. So you just combine those two things together. You get 2,000,000 p over q times p plus 1 cubed. And so long as p is positive and q is positive, this thing will always be positive. And they are. So it works out fine. You don't really have to think about that. Just if you get an answer and you're like, is this thing always positive? Yes, you know, you're probably in good shape. Okay, so we have an elasticity function, but it's in terms of two variables, so we're going to have to mess with it a little bit. So let's just make sure we know what we're doing. Find the elasticity when p is $39. So the first thing we have to do is figure out just the corresponding q value for p being $39. So that's just like f of 39. That's just whatever point on the curve we're at. So remember q, we figured out was 1,000,000 over, okay, 39 plus 1 squared minus 1. So just plugging it back into the original function. When we're charging 39 bucks for our product, our demand is 624 people, um, or units, which might seem like a lot, but once we look at the graph of this thing, back when we were charging really cheap prices for it, our demand was like 1 million, right? So there's an equilibrium in there somewhere, but it ain't this. Why? Because, okay, so here's the elasticity. So it's now we're doing the elasticity. So it's 2 million times P, which was $39, over our demand Q, which was 624 units, times the price plus 1 cubed. Calculator time, right? Just punch all that into your TI or your computer or whatever, and you should get 1.95. So what does that mean? That means we're in elastic land because it's greater than 1. So that's generally kind of bad. Because if we raise our price even like a fraction of a percent more, we're going to lose more than that fraction of a percent of our demand. Okay, so that's all I'm really going to ask you, just to interpret it. Is this elastic? Is this inelastic? Is this right in that sweet spot? Unitary elastic, right? Inelastic, like if you charge almost nothing for your product, it's going to be pretty inelastic because, okay, if you charge 5 cents for something and you raise it for 6 cents, you're probably not losing many people, right? But that's still not necessarily good because you're only selling your product for 6 cents. I guess you're not going to make any money, right? So you don't want to be too far in either direction generally. Here's the graph of that demand. So, right, it's one of those things that descends a lot. So like what I was just saying with the 5 cents, 6 cents is kind of towards the beginning. Demand is huge, but you're still like, you're not making the money you should be because you're not selling it for enough. Now, if you get down to where we're at now, so I plotted the point 39, so price is 39, demand is only 624 there. So we're selling our product for relatively a lot of money, but we don't have that many customers. So if we raise our price by 1%, we're going to lose more than that share of our demand. So you probably shouldn't. And that's generally the case. The higher the price is, the more elastic it is. And the lower the price is, the less elastic it is, because 1% of a dollar isn't that much, but 1% of $1,000 is a lot. And that's when you start to lose people. Okay, it gets a little tricky now, but this is important. So revenue is price times demand, right? We've been plotting demand versus price. The actual revenue is just the product of those two coordinates. It's P times Q. How much it costs times how many people buy it. So that. So we're going to think of them both as functions of price. So if we think of demand as a function of price, so Q equals F of P, that's how we were doing before. And then just also think of revenue as a function of price only. So it's like revenue is a function of P and Q, but Q is also a function of P. So it's like the product rule, right? It'd be like X times e to the X or something. So we're going to use implicit differentiation on that, on R equals P times Q. This is going to get a little mathy, but I'm leading to a very important thing that is going to come up again. Okay, so differentiate both sides with respect to the variable P. The derivative of R is just dr dp. We don't know what that is. Remember, this is implicit differentiation. And now we have to use the product rule. So it's the first function times the derivative of the second function. The derivative of Q is just dq dp. That's what it is. We don't really know what Q is explicitly. We just know it's a function of P. And then plus, okay, the derivative of P is just 1, and then times the second function, which is Q. So P is our X here. When we say think of things as a function of P, just P is your X. You can replace this all with Y and X if it makes your life easier. Okay, so clean that up. So that equals P times dq dp plus just Q. And then here's a trick for what I'm getting at. If you're wondering why is he doing that, why is he multiplying the first term by Q over Q? Because it works, because it's something that somebody smarter than me figured out, so don't worry about it right now. It's just how we get from point A to point B. So we're going to take that P times dq dp, we're going to multiply it by Q over Q. We can do that because Q over Q is just equal to 1. Okay, so I know it looks weird. Now the point of that is, maybe you'll see in the next step, I'm going to factor out a Q. Now every term has a q in it, so I can take that out front. So I'm going to factor out a q from both of those terms. So that's q times p over q times dq dp plus 1. Look at that first term in the parentheses. P over q times dq dp. What's that? Right? That's a thing. Wait, that's just like elasticity, right? Only it's not negative. So that thing, that term right there is negative n, or negative eta. That's just the elasticity, but without the negative sign. Okay, so that's what I mean. That's exactly the same as eta, just missing a negative sign. Okay, so we can replace that term with just negative eta. Like that. Okay, so what the heck are we doing again? The change in revenue with respect to price. That's what DRDP is, right? If we change the price a little bit, our revenue changes a little bit. Is it going up? Is it going down? Well, we want it to go up. And in fact, we want to find the spot where it's at its maximum. Okay, so we have the derivative, the change in the revenue with respect to price. So when we change the price is Q times negative elasticity plus 1. And just think about this. If DRDP is 0, what does it mean for the derivative to be 0? We're probably at a max, right? And that's good. So if n, I'm just going to call it n from now on. If n were exactly 1, that thing would be 0. Agree with that? It's q times negative 1 plus 1, right? That's what we call unitary elasticity. So the whole point of this is to say, oh, what is that sweet spot of unitary elasticity? That's where r prime basically is 0. And that's where your revenue is optimal. All right, so the change in revenue with respect to price is 0. So in other words, if you change the price a little bit at that point, your demand is basically going to change exactly the same way. And if you lower the price by 1% of that point, your demand is generally going to go up by 1%. So you're in a good place, right? Because you're in the place where your change in what you're charging is exactly equal to the change in your demand in both directions. So that's good. So that's where you want to be, right? That's where you want to be, where that's the proper price for that demand, because revenue is optimal. And we'll do a math problem and we'll look at R, a revenue function, and we'll see that, yeah, that hits a peak at exactly the moment where we have unitary elasticity. A lot of big words. This is a hard math problem. So here we go. So same deal. I'm giving you a demand function. It's given by P equals 120 times the cube root of 125 minus Q. So we've discovered that the price we're charging is 120 times the cube root of 125 minus whatever our demand is. Notice this means our demand is never going to be more than 125, because that would make that thing negative. And of course, it's not going to be less than 0 either. So I'm just going to ask you a bunch of questions about this. I've given it to you with like P kind of written as a function of Q, so we got to do a little bit of work off the bat. I just did that because that's how the stuff in the book is, so that's how the stuff in the homework is, so you're going to have to do this. So first, let's just find an expression for the elasticity of demand. So it's always that. It's negative P over Q times dQ dP, and right off the bat we say, ah, man, well, you could rearrange that thing for Q, to solve it for Q, and then do the derivative normally, or you could just do the derivative right now by implicit differentiation, because you know that Q actually is a function of P. So I'm going to do it that way. Yeah, okay. So first, so we want everything in terms of Q. I'm going to do this in kind of a not peculiar, but just a particular way, just because this is how the book does it and this is how the homework does it. There'd be different ways to get to the thing I'm looking for here. But it is simpler in the end if we just have only Q in our elasticity and our revenue functions. It makes it simpler to deal with. So I'm just going to start replacing P stuff. So right off the bat, I can easily replace P with what I know it is, 120 times the cube root of 125 minus Q. So that's our N so far, but we need dq dp. All right, so we're going to do it. I don't think it's a harder of a way, but it's a more calculus-y kind of way. We're remembering that Q is a function of P, so we have to observe like the chain rule here. So starting with what we were given, P is 120 times the cube root of 125 minus Q. Differentiate both sides with respect to the variable P. So in other words, the derivative of the left-hand side is just 1. So P is like our x. The derivative is just 1. The derivative of the right-hand side is a different story. So first you use the power rule on that cube root. So it's 120 times 1/3, 125 minus Q to the negative 2/3. That's a negative 2/3. Those don't always look so good on PowerPoint, but right, you know what that is. That has to be a negative. That's 1/3 minus 1, so that's negative 2/3. Times the derivative of the inside. So if you think of Q as a function, the derivative of 125 minus Q, well, the 125 goes away, the negative just comes along for the ride, and the derivative of Q with respect to P is literally dq dp. That's what it means. You could call that Q prime if you want, as long as you know that Q is a function of P. If it's simpler for you, call it Q prime. Okay. So the next thing in implicit differentiation is to solve that equation for dq dp. So from here on out, it's just algebra. So I know I kind of did a lot in that one step. So, pause this and be sure you know what I just did. If you want, again, you could solve this for Q in terms of P and then do the derivative. It wouldn't be faster, but it might be easier. Okay, so just cleaning it up. 120 times 1/3 is 40. We have that negative sign as well. And now we just got to start moving everything except that dq dp to that other side. So I did it. I divided by 40, and then I essentially I divided by 125 minus Q to the negative 2/3, but all that happens when you do that is the exponent becomes positive. Thinking about taking, like, if it was just x to the negative 2 and moving it to the other side, that's the same as just multiplying by x squared. So I did everything all at once. So it's negative 1/40 times 125 minus Q to the positive 2/3. So that's now, was kind of in the denominator, now it's in the numerator. Okay, so that's as good as we're going to get for our expression for N, or for dq dp. Stick that in to our earlier expression for N. We had, okay, it's the thing we already had, which is negative 120 times, I wrote the cube root as 125 minus Q to the 1/3 over Q, times the thing we just got, negative 1/40 times 125 minus Q to the 2/3. I told you this got a little ugly, but it's actually about to clean up nicely. And that's, maybe you'll kind of see why I did it this way in a second, because the result is pretty simple. Okay, so what the heck is happening right now? Those two negatives cancel each other out. The 120 and the 40 divide to just 3. And then a really nice thing happens where 125 minus Q to the 1/3 times 125 minus Q to the 2/3. 1/3 plus 2/3 is 1. So that turns into just 125 minus Q. So here comes all that. Right, the negatives go away, we just have a 3, and then the exponents actually very blessedly went away as well. So it's just 3 times 125 minus Q, and the only thing left in the denominator is the Q. And I'm just going to go ahead and simplify that to 375 minus 3Q over Q, just to make it, I think, as clean as possible. Okay, so what the heck did we just do? That's the elasticity. So for demand Q, the elasticity is going to be 375 minus 3Q over Q. Okay, Now we want to find the demand needed for unitary elasticity. So what we've seen is there's two ways we can do that. We can see where n equals 1, or we can find the revenue and optimize the revenue. So we could find the revenue, which is just P times Q, do R prime, set that equal to 0, solve. So that sounds like a little more work. And you'll see in a second, I hope, why I did that the way I did it. So what I have now is our elasticity just in terms of a single variable Q. So it's actually pretty darn easy to just set this equal to 1 and solve it. Right, unitary elasticity occurs when the elasticity is exactly 1. So you see how easy that is? Just 375 minus 3q over q equals 1. That's very easy algebra to get this now. Whereas if it was in terms of two variables, or if it was in terms of just p only, it might be a little trickier. Okay, so just multiply both sides by q. 375 minus 3q equals q. Add 3q to both sides. That gives you 4q equals 375. Just divide by 4. Q is exactly 93.75. So it might not make exact sense for a demand to be that, but if it didn't, we just round it to 94 anyways. Okay, so that's it. That's what we want. So when Q is that, the price, we want to set our price point as well for optimal revenue. That's 120 times the cube root of 125 minus 93.75, which turns out to be about 377.98. So that's how much we want to be selling our thing for. That's where we get that perfect elasticity, where if I charge a little more, I lose a little bit of people, and if I charge a little less, I get a little more people. Right, but it's right at that kind of sweet spot. So all we're going to do with the revenue function, again, you could do the previous part with the revenue function. Let's just look at it though. Let's make sure it makes sense. So R is just P times Q. So P was just 120 times the cube root of 125 minus Q. Since we've already got, good point, since we already had our elasticity function in terms of Q, I would like to get this in terms of Q too, because that way, like, if we were to graph them and compare them, it'd be tough because these are big numbers, but you'd be on the same scale. So you'd be looking at like the scale of demand. Either way, we have our optimal price and our optimal demand, right? So it'd be fine. So you could do this either way. I just already had stuff in terms of Q. I already had P in terms of Q. That's what I was given at the very beginning of the problem. So to find the revenue, why not just multiply that thing by Q? So there's a Q in there. It's 120Q times the cube root of 125 minus Q. Let's graph that bad boy. So we're just going to use the graph. Rather than take the derivative of that thing and set it equal to 0. That would be a little nasty involving the product rule. So I just graphed R, and I know it's easier to graph stuff like this on a computer than it is on a calculator because the numbers are so big. And then I just punched in, okay, when demand is 93.75, that's what that point is. So the revenue right there is $35,435.28. So that's it. That's our optimal revenue at our sweet spot, our point of unitary elasticity, when we're charging $377.98 and our demand is about 94 units. So in this case, I probably would just say use some kind of graphing software or something on your calculator to find the maximum revenue if it was, you know, just overly complicated. And that's elasticity.